Our next speaker today is Timothée Marquis from Louvain, who will speak about amalgams of rational unipotent groups and nilpotence.
Thanks for the invitation. So yeah, I want to tell you about residual nilpotence of certain amalgams of groups. This is transferred with the Amalgams. And since it's a kind of question that has a relatively long history, I just want to start by putting things in context, giving you some context. So let me start, just to be sure, by following the definition of the residual property. So given a property P of group, the group G is called residual P, like finite or residual nilpotent, if every non-trivial element of your group survives in a portion of that group that has property P. So every non-trivial element has a non-trivial image in some portion of G with property P. And a standard question concerning residual properties of groups is the following. Imagine you have three groups A, B, C. We see a subgroup of A and B that have this property B. And then the question is, does the amalgamated product of A and B along C is this amalgamated product residual? So this is a kind of standard question that was originally motivated by the theorem of Magnus from 1935, telling you that three groups are residually nilpotent. Actually, even residually important. So every non-trivial element of the free group survives in a quotient that's nilpotent and does not have any torsion element. And since this notion will come back, I will abbreviate it RTM Fn for residually important free groups. So since that's one property that I will focus on in a moment, I just want to maybe rephrase for you what it means in formula to be residually nilpotent. So I can fit some notation. So I will denote by gamma n of G the lower central series of G. So gamma 1 of G is just G, and gamma n plus 1 of P is the subgroup generated by all the brackets, the commutative brackets of elements in G and gamma n of G. So that, well, G is nilpotent, of course, if gamma n of G is trivial for all Laplacian of n. But what does it mean to be for G to be residually nilpotent? Well, this is the same as note gamma infinity of G, which is the intersection of all these gamma n of G. This intersection should be trivial, right? Because if you have a quotient, an important quotient of G of nilpotency class n, or say n minus 1, then by construction, the quotient map to this nilpotent quotient factors through G mod gamma n G. And so, in other words, an element of my group is skilled in every nilpotent portion of G, if and only if it's filled in every nilpotent portion of G of the form G mod gamma in G. And this is the same as belonging to this intersection of the gamma in G. So this group is not residually nilpotent if some element, some non-trivial element survives in this intersection. Okay, so we'll come back to that a bit later, but I continue with some milestones after Marquis and a theorem of Higman, who studies a finer property than being nilpotent, namely being a finite P group for some prime P. And so, 1964, with a theorem stating that if you have two finite P groups, you have two finite P groups, and you take C, a subgroup of A and B, then actually Higman provides a necessary and sufficient condition for the amalgamated product to be residually finite P group. Now I will not tell you exactly what's this necessary and sufficient condition is, but I will just put when necessary conditions, when C is cyclic, then this amalgamated product will be residually a finite P group. But you have a characterization, and
could you please remind what a possible example when this group is not residually P? Group?
So one example will come. But so the characterization is in terms of if this will be residually a finite P group if A and B have a G series that have the same intersection with C. Yes. And this kind of characterization has been generalized to arbitrary fundamental groups of graphs of the finite P groups. So here we have a general statement for being finite P groups. Now, what about being residually nilpotent? Well, for residual nilpotence, things are more complicated. And I want to illustrate this with an example. If you have different primes, P1, P2, then the claim is that actually if you take the free product of the cyclic group of order P1 and P2, this is not residually nilpotent. So it's not true in general that the free product of two nilpotent groups will be residually nilpotent. Whereas this is true, for example.
I couldn't follow the notation. You take a free product just of two finite groups, one.
So this is the cyclic group of order P1, and this is the cyclic group.
Cyclic group P2, and it's not residually nilpotent.
And let me justify why this is the case. So suppose this is the case. Let's write, let A be a generator of the cyclic group, CP1, B a generator of CP2. And now I'm looking at the commutator, the group commutator of A and B, so which I view as an element of this free product. Certainly that's a non-trivial element. So if this free product were residually nilpotent, this element would survive in nilpotent quotient, will survive in a quotient that is nilpotent. But note that this group is finitely finitely generated. And finitely generated nilpotent group by a result of Hirsch is residually finite. And so actually G would suffice in a finite quotient of my nilpotent group. And so in a finite nilpotent group. But of course, finite nilpotent groups are products of their P zeros. And so my element G would also divides in a finite P or some finite P. Say big P. And now if you look at the image of G in this finite P group, well, by assumption, P1 and P2 are distinct primes, and so they cannot be both equal to P. So let's say P1 is not equal to P, and so A, you look at the image of the generators here, A is of order P1, and so it cannot survive in a finite P group.
But the unipotent group, it's residually P, but this P can depend on an element. Now, if you take a direct product, for example,
it's just that here I fix my element. So this element will
survive for some P.
In some P, for
yes.
some P.
But what is your element that you take?
The commutator.
The commutator, the two and yes.
So for this element, at least one of A and B will be mapped to the previous element, and so G cannot survive. Okay. So that's what it is, but not all is lost. For about residual nilpotence, since you have a theorem of Marzev from 1949 that tells you that the problem is the torsion here, and that actually if your two groups A and B are residually, or even residually, but torsion-free nilpotent, then their free product is also residually torsion-free nilpotent. Okay. So this is about free products. Now, what about amalgams? Then, in this case, I want to mention an example constructed by Bomslag, 1962, which shows that things can also get complicated even if you're looking at torsion-free nilpotent groups. Namely, he constructs an example where A and B are two copies of the Heisenberg group of the Z. So this is this presentation, right? And then he shows that we can construct an amalgamated product along a subgroup C. C is actually isomorphic to Z squared in this example. That is not residually nilpotent. It's actually not even residually finite. So clearly you cannot do anything you want.
And if you reduce mod P, this is an example for Anna.
Yeah, that's what I. But now I want to jump in time, and so forget maybe intermediate results or other results in other direction. So I will focus on this question, but you have other interesting results, and notably the result of Andre about the potent residual nilpotence of the free cube groups. But about amalgamated products of groups, what I want to mention is this theorem that these natural Nessels-free conditions for an amalgamated product to be residually nilpotent. So this is the case if, well, first A and B could be nilpotent, And as shown by the example above, you need to assume torsion freeness. In second condition, you need some condition also on C with respect to A and B, as shown by Baumschlag example. And so here, natural condition is that C is retract of A and B, which is not a condition that's satisfied in Baumschlag example. So this simply means that A splits as a semi-direct product of some subgroup with C and say same with B. And then we put a third condition, which the two first conditions are, you certainly cannot remove them. But we also assume that C is abelian, which is probably not, most probably a redundant condition, but this greatly facilitates the commutator computations that are involved in the proof. But one of my PhD students is currently looking at generalizing this theorem. But in our paper, our focus was a bit different. So our focus was more to shed some light on an intriguing phenomenon that occurs when you look at residual nilpotence of some higher rank amalgams of groups. And I want now to explain you what these amalgams are. The definition, consider amalgams very simple torsion-free nilpotent groups. And so they will be defined over Q as follows. So I will look at a bunch of copy UI of Q plus. Index is on finite set I, let's say. And then I will look at an amalgamated product of these copies of Q. And for this, I will explain you first what are the puzzle pieces of my amalgamation. So there are four of them. Then I will give you the presentation. So I will note Q, A2 of Q. But I will only consider two copies of Q for the moment. So it's U1 and U2. Now we look at the free product and then quoted on by the normal subgroup generated by U1, U2, and U2, U1. So this is just the Heisenberg group over Q. So this is just the matrices that are unipotent and upper triangular in SL3Q. And so just for the notation A2, so this SL3Q is actually the Chevalier group of type A2 over Q. And this is the unipotent radical of the standard Borel subgroup of this Chevalier group. And the other one will be, and so if you want to associate the link diagram to that situation, you will have a simple edge between U1 and U2. And the other group will be defined similarly with other rank 2 Chevalier groups. So you have of type B2. So again, this will be free product of these two copies of Q quotients out by the normal subgroup generated by, again, you have U1, U1, U2. And then U2, U2, U1 is not trivial anymore, but it's central, so it commutes with U1 and it commutes with U2. So again, these actually coincides. You take the trivial groups of type B2 over Q, and then you look at the standard model subgroup, and then inside you just take the unipotent radicals, so you remove the torus, and this is the group you will get, where U1 and U2 stands for the simple root groups. So here you have U1 and U2 in this example. You're not fond of field theory, then the presentation. And so here, the associated zinc diagram would be a double edge between U1 and U2. And then I will not give a presentation, but you have similarly a group of type G2, so which will be associated to a triple edge. And what do I forget? Oh, and just zero when you don't have an edge. So that would be A1 times A1. So this is just the free product of U1 and U2 mod the commutator of U1 and U2. This is the direct product of this. So these are my puzzle pieces. And now, how do I construct my amalgams there? I start with a so-called two-spherical linking diagram. So what's that? Well, it's simply a graph. Simply a graph with vertices are the elements of I, or you can think as a UI, and where you put and where you have edges of one of these four kinds. So either you have no edges, no edge between two vertices, or you have a simple edge, or a double edge with an arrow, or a triple edge with an arrow. And you construct any graph you want this form. And then to this setting, we associate, so let's call this gamma, its graph. We associate the corresponding amalgam, which I will denote U gamma of Q, of the subgroups UI. So that are here, one for each element in my indexing set I. So these are copies of Q. And I will not define formally this amalgam, but I will just give you an example and you will understand how it works. So, for example, what happens if you take a graph, which is just a triangle with three simple edges, U1, U2, U3. What is the amalgam I construct? So the group here is U gamma 1 of Q, which I will is usually also denoted by U A to tilde of Q, because that's the linking diagram of type A to tilde. Anyway, so this will be a free product of the three copies of Q, U1, U2, U3. And then you portion out by putting for each pair of UI, Uj, you add the relations that I pasted here, given by the edge. So here you have a simple edge, so you have an A2, and then you will add these relations between U1 and U2. And the same relation between U2 and U3, and same relation between U1 and U3. So here, for example, this will amount to looking at all the relation of the form UI in J, or any I in J distinct between 1 and 3. Okay, if I had replaced this edge from U1 to U2 by a double edge, then instead of these relations, I would have put these relations between U1 and U2 in this amalgam. So note that if I forget about the relations between U2 and U3 here, what I get is an amalgamated product of two copies of the Heisenberg group. So the one generated by U1 and U2, and the one generated by U1 and U3. So these are two copies of this Heisenberg group, amalgamated along U1. And so this theorem here tells you that this amalgam, if I forget the relation between U2 and U3, this will be residually nilpotent. And it will be actually residually torsionally nilpotent. But actually this one is not residually nilpotent. And if you put a double edge here, it's still not residually nilpotent. Let me give you another example. If I look rather at the square, let's say double edge here, 1, 2, 3, 4. So I will not write presentation. So you gamma 2 of 2. This is gamma 3, the quotient of the three products of U1, U2, U3, U4 by the relations you see for each edge, right? And if you have no edge, it means that U2 and U4 commute. This is this relation. This one is residually torsion-free nilpotent. If you put a triple edge, then it's not residually nilpotent. Now I want to state a more precise theorem. And make what's happening. I want to first state a more precise theorem in the case of A to tilde, in the case of this triangle. So let's proceed step by step. So a fact, which you can easily verify, is that there is a group morphism from this amalgam. You make tilde Q. You find there above to SA3 QT. So to SA3 QT, and it's the image is almost everything, but it's not quite. So the image is the diagonal. You have things that are 1's modulo T. Below the diagonal, you have things that are 0 modulo T, and here you have everything. So the image of this morphism is the subgroup of matrices that are upper triangular and unipotent modulo T. And what is this morphism? So if I denote by xi the parametrization of the ui as copies of Q. It maps x1a to 1, 1, 1, and when you have an A in position 1, 2, x2a 1, 1, 1, and then A in position to 3, and then x3a 1, 1, 1, and then in 18 position 3, 1. This you just have to check that the relations are satisfied, and you have to, you see that you have a morphism. And the theorem I want to state is that the kernel of this morphism coincides with this gamma infinity, this intersection of all the gamma n of ua to q. So in other words, that my amalgam is residually nilpotent, even only if phi is injected. Right? Residually nilpotent meant that this gamma infinity was triggered. And the second part of the theorem is that if you consider the subgroup, let's say H, generated by U1, U2, and U1, U3, or U2, U3, it doesn't matter. I have the same thing in my notes. So this I view as the subgroup of this amalgam. So recall that in this amalgam, U1 and U2 generated a copy of the Heisenberg group over Q, and same for U2 and U3. So the bracket of U1 and U2, this is a copy of Q. This is a copy of Q. This is the copy of Q here in position 1, 3. And this is also a copy of Q in this Heisenberg group generated by U2 and U3. And what I claim is that these two copies of Q, they generate their free product in my amalgam. I will write like this. But their image is just a three-dimensional Heisenberg group. So these two copies in the image there, they just generate this Heisenberg group. So in particular, there are many elements in this kernel, and you can give explicit elements in this kernel. So for example, in particular, gamma infinity of Q A to Q that Q contains all the elements where we take U1, U2, bracket, U1, U2, U2, U3. Right? In the Heisenberg group, you have X and Y, the generators, and here you have the X, X, Y. This is skipped in the Heisenberg group. But of course, X, X, Y in the free product of X and Y, this is not skipped. So every element in there belongs to the kernel. And so indeed, every element in there witnesses the fact that UA to theta Q is not residually important. As a side note, the proof is more conceptual, that we first try to just to prove that it was not residually important to just give to construct some elements, because saying that such elements are in gamma infinity, this means that you can modify an element in there, so it's a concrete element using the relation to show that it's in gamma n for each n. But that we're not, we cannot manage to do it by computation. But nevertheless, this is cool. And now I want to state, before telling you about the proof, the more general version of this, which is, well, maybe I could make one remark, is that one inclusion here is obvious, namely that namely that gamma infinity of this amalgam is contained in the kernel, and this is simply because this is known to be residually important. So the gamma infinity here is mapped to the gamma infinity here, which is trivial, because this is residually important. And so the information is in the other inclusion. The kernel phi is contained in all the gamma n. And so now I want to tell you more generally for my more general amalgams what happens more generally. And for this, I just want to rephrase the information of the two spherical linking diagram. This can be encoded in a slightly different manner using Cartan matrices. So this is the same info as matrices Aij indexed by the indexing set I. So this is so-called two spherical generalized Cartan matrix. So this is a matrix like a usual Cartan matrix with the twos on the diagonal and then non-positive integers off diagonal. And then the fact that it's two spherical means that the entries Aij and Ji are fully given by specifying that they're either 0, 1, that these products are 0, 1, 2, or 3, where this 0, 1, 2, or 3 is the number of edges between I and J. So this is just an equivalent way to formulate this datum, which will be more convenient for me in a moment. And so I will also then denote the corresponding amalgam as UA instead of gamma U. So this was gamma. Okay. And then the theorem is that you also have a map phi from this amalgam UAQ to a certain group U plus AQ. And that the kernel of this map again coincides with gamma infinity of UAQ. And this group U plus AQ, well, that's unipotent radical of the standard positive Borel subgroup of the minimal cosmetic group of Q. That's a group which is known to be residually important. That's all you need to know. And so, again, we know that. So this map, in this A2 picture, this is this map. That's exactly this map. In general, you also have it, and so it's known that gamma infinity of UAQ is mapped to the identity here. This is known to be residually important, but again, the information is that it goes in the other direction. And the following are equivalent. The UAQ, or amalgam, is residually important. Second, that UAQ is residually token-free important. This is basically just because we are over Q that we have these equivalents. And then the deciding factor is that the matrix is free spherical. Which means that it's a diagram of my linking diagram with three vertices are really linking diagram of finite type. So of type A3, D3, C3, or A2 times A1, B2 times A1, or A1 times A1 times A1. So in these examples, here, if you look on this picture, if you take only three vertices, you see that you always get either something of type A3, B3, or C3. And so this will be residually torsion-free nilpotent. If you consider, if you put a triple H, then that's only true anyway. And in the few remaining minutes, I want to give you an idea of the proof, since it's relatively simple and conceptual, and it needs two ingredients, namely, first, that if you have a group H, with group H you can associate the neuron, a Z algebra, defined as the successive quotient of the gamma n of gamma n plus 1. So this is a Z algebra with respect to the bracket G gamma n plus 1 H. So if G is in gamma n of H, when you look at the bracket, H is in gamma n of H. This bracket is the commutator bracket of H and G, but gamma n plus 1 n plus n plus 1 H. And this, the fact that it's that satisfies the Jacobi identity, it just follows from the usual commutator formula you have the whole width and so on. And the second ingredient is that we have a Lie algebra which are denoted by n plus AQ, and which is the algebra defined by this presentation, which is the positive part of the Gatsby algebra of type H, but it's generated by this Chevalier generator CI, and then you put the set relations where the AIJ are in the Cartan matrix. So this is a presentation of Lie algebra. And what you do is, well, you have this map phi from UV AQ to this relatively important group of UV AQ. And then, of course, phi maps gamma n to gamma n. It's morphism, and so it descends to the morphism of the corresponding Z algebras. And this is actually subjective. And on the right side, you can continue this arrow, and this follows from the Moody theory, that you have an arrow from this Lie algebra to this Lie algebra, natural map. And what we would like to have is also an arrow on the other side, where you map EI to XI1 gamma 2. So all you have to do is verify that the relations here, they're verified by the UI and UJ in this, but the amalgam was defined in a very similar way. So it's not such a surprise that these relations here are satisfied also in this Lie algebra. With one little detail is that it's a presentation of the Q Lie algebra, and here you only have the Z Lie algebra, so we use the universal property in Z Q Lie algebra, but that's what they prove, that actually these are Q Lie algebras. And so what this means is that actually EI here, it must be EI here. And so actually all these maps are isomorphism. So L5 is an isomorphism. And now we are done because now suppose that you have an element which is not in gamma infinity of my amalgam. And I want to see that it's not in the kernel of phi. That's the implication I have to check. Then if it's not in gamma infinity, then it's in some gamma n and not in gamma n plus 1 or some n. But then this means that the element, if I do G gamma n plus 1, this is an element of the Lie algebra of my amalgam, and this is non-zero. But as L phi is an isomorphism, this is also non-zero. But this is just by construction of L of phi, this is just phi of J gamma n plus 1 with U plus LQ. In this Lie algebra, and so saying that this is non-zero, this is to say that phi of J is not in gamma n plus 1. And so in particular, phi of J is not trivial. And so that's how it works. And to conclude, you show that E is free spherical, A is free spherical if and only if phi is injective. And then that's how you can conclude. Thanks for the attention.
Thank you.
Questions and comments?
So I have a comment that you write gamma infinity, but it should really be gamma omega for the first ordinal, because then it continues, right? There's gamma omega plus 1, which will be commutators of gamma omega with G, and so on. So can you say exactly what is the depth at which these amalgams become trivial? Presumably something like it would be 2 omega, well, omega times 2, sorry, for theorem B, because you have a Heisenberg group which eats another omega. But if you write ordinals instead of just infinity, then it becomes a richer question. How many steps of taking intersections and taking commutators? Well, intersections for limit ordinals and commutators for one step do you need?
Yeah, that's not something I thought about.
But I didn't follow. So the groups are finally generated, right? So
yes.
How you can see something more than omega?
Well, there are lots of ordinals which are still countable.
Yes, but how you can see?
Yeah, so for a limit ordinal, gamma alpha is the intersection of gamma beta for beta less than alpha. And for a non-limit ordinal, something like alpha plus 1, it's the commutator of gamma alpha with G.
But if you have something not reasonably finite, would it be by definition that gamma omega is already?
You have gamma omega, which is the intersection, and then itself doesn't have to be perfect. The intersection can have the property that if you take the commutators of that.
Can you give an example? Yeah.
So not really, but there are examples of, say, two related groups for which it's well computed that you have to go to, what is it, omega squared or something like that. There are papers by Mikhailov, for example, on exactly computing the, nilpotency ordinal or so.
Even for such amalgams?
No, for this, I don't know at all. I was just thinking that why write infinity when the real question should be how many ordinals do you need? Well, how many steps of ordinal induction do you need?
I have a very naive question. So for some amalgams, you characterize which of them have some readily defined properties. Are there some more general classes of groups where it could be challenging to understand if well, in this spirit, I mean, of course, we know for hyperbolic groups, the residual finance is simply is a difficult question, right? But more in the spirit of your groups, you consider other some classes of groups where it's challenging to understand whether they have such residual finances properties, like in the early
our real goal was and still is to look at the same amalgam but over finite fields, over FP.
Yes.
But so far, the Q is the only case where the proof works. So
and for P, other conjecturally the results are similar to what you put for.
Yeah. So there is some interality properties. So although you cannot formally deduce anything from them, but so we believe that there could be the same distinction. Yeah, modular small primes or something like complicated. But so the key idea is this sequence of maps, which you also have if you put FP here. And yeah, so this is an FP the algebras, and you can define all these maps, but there is a subtlety is that here, if you define this Lie algebra over FP, in general, you will have torsion elements. And in this algebra over FP, it will not be the same. It will be actually obtained from this one over Q by taking a Z form and then tempering over FP. And so here you will kill all the torsion elements. And so understanding the torsion elements is the difficult part. And one hope is that we could use this over Q to go to Z localized at P and then to FP. Yeah, that's the goal, but that's much more.
Any other questions?